I just read it up a bunch of times.
I'm just being lazy at this point because I don't want to get it up.
Yeah.
So if you don't eat breakfast, you only eat like 2 meals a day.
Sometimes one, mostly
Wait,
two.
how are you?
Because I don't like eat meals because I work from 4 to 8 a lot of days. So it's like if I eat dinner, I'll go home and like eat a snack or something. But my eating.
Functions. Yeah, we kind of went backwards right into chapter 1, just trying to get those inverse functions here. Did we?
Should not. Oh wait, I guess yeah.
Are those like the sine -1?
Sine -1, yeah,
You're
From
annoying
trig
with
class.
other things. I don't like those.
Ooh.
You don't like the inverse functions are messy.
Yeah, they just don't
Okay.
look. They don't look so ordered.
So,
Especially inverse cosecant. No, I do
No.
not want to see that ever.
okay. I will have to show it to you once then. Okay. Let's talk about inverse functions and slopes. How about that? Inverse functions and slopes. Let's talk about that first. So I got 2 inverse functions. Let's go with a nice generic one called x squared. I like x squared. X squared comes down like this, boom, and we go like this. And we have ourselves a dot at 0, 0. That's nice. And let's see, we have a dot at 1, 1. That's nice too. And then usually the dot at 2, 4. Okay, so let's review just a few little things about inverse functions. What is the inverse function of x squared? Do this one. Haha, trick question. There is no function of x squared.
Yeah, because it's not gonna be. Isn't it square root of that? When we cut it.
Yeah, so first things first is remember the vertical line test from a long time ago? Vertical line test proves that something is a function. So if you go down, up and down like this, it only hits at one spot. The horizontal line test is to prove that the inverse function is a function. Does this guy pass a horizontal line test? No way. Okay, so if it doesn't pass a horizontal line test, what can we do?
We can't.
Oh, cool.
Cut it in half.
Or restrict the domain. That's what we do. So first of all, we're going to restrict domain. So then we're going to do it like this. We're going to chop this off right here.
Wait, so vertical is for seeing if it has an inverse, and then horizontal is for seeing it's a function.
Yeah, perfect. So if the inverse is a function.
Okay.
So horizontal line test, inverse is a function. That's kind of nifty. All right, so we can restrict our domain if we wanted to on anything, right? Sometimes restriction of domains are based upon physical things in our world, right? So like time can't be backwards, right? So time's going to be t is equal to 0 or further, right? So stuff like that, right? And in this case, if we want to create something, and so with the trig functions, remember we used to chop off the domain, right, until we were able to switch it to an inverse function. So that's all. You can get an inverse function of x squared. That's no problem. I'm sorry, you can get an inverse of x squared. It just won't be a function. We good? I can plot the inverse. I just switch x's and y's, and voila, I got myself an inverse of x squared. It won't be a function. Okay, so my domain restriction is from 0 to positive infinity. That's my domain restriction. And if that's the case, voila, I have myself now an inverse function. This might be in 2 parts as well. Let's see how we do it. So I'm going to list this guy as, I should list it as inverse. Remember how we do like a little -1 over here? So the inverse function of x squared is the square root of x. Everybody agreed?
Wait, so if we take the derivative of an inverse function, we do f prime of the negative.
Oh yeah, this is gonna be fun for notation purposes. Oh wow. So 0, 0 is still our dot here. 1, 1 is still our dot here. And then 2, 3, 4. Now we have ourselves a 4, 2 over here. And voila, it turns like this. Okay, what we're interested in is this whole concept of slopes, right? This trig, calculus is interested in slopes. So real quick here, talk to me. can you guys give me the slope? And you guys slow me down, okay? Because I have written, I'm just having fun, okay? So can you guys give me the slope of, let me put it into different colors so we see it. This one. Give me the slope from here to here. Let's do this one first. Boom. From 1, 1 to 2, 4. I should do one more thing here. Let me just label these guys as 0, 0. This is 1, 1, and this is 4, comma 2. Cool. Back to my changed color. All yours. Da, da, da. This is so much fun. As we get into the trig functions, that'll be fun.
So we're just finding.
Yeah, give me slope real quick here. Should be easy. Answer is 3. Yeah, 3 or 3 over 1, right? 3 over 1. Okay, so hold on. That's my original function, right? Let's flip it over. Give me the slope of this guy. 1/3. Okay, 1 over 3. Everybody agreed there? So we're kind of seeing a little something here. Okay, let's just not pick just one point. How about this? How about we'll do another line? How about from here to here? What's the slope here then?
2 over 4.5. Wait. There, yeah, 4 over
4 over 2?
Yeah.
4 over 2, and eventually just 2, right? Cool. Okay, so if I go over here then,
it would be 1/10.
okay, so we're getting our sense of things. We good? So inverse functions, the slope of inverse functions are reciprocal of each other. That's cool. Do you guys remember back in algebra? Do you guys remember parallel lines had same slope? Remember that? Perpendicular lines had yeah, negative reciprocal or opposite reciprocal. So now we have this third one. Inverse functions have just reciprocal slopes. That's it. That's cool. Okay. That's fun. That's our sort of our quick investigation into things here. So now the question is, how do we think about the derivative of this stuff here? It kind of helps if we go to our definition of, let's see, what happens, trivia question here from Algebra 2. You guys talk to me here. F inverse of x is equal to what? So if you take a value in the inverse function, take the inverse function of it, right? And then you plug that into the function itself, what do you get? Kind of fun thing. Uh-huh.
Does it like go back? to the initial-
It would just be x.
Just be x. I agree. Say, do you agree?
Yeah, that's what I was
Okay.
trying to say, but-
Okay. Yeah, so real quick here, just take a look at it here from Algebra 2. If we were to plug in a 4 into here, right?
They just switch later, so.
That would be a 2, right? Because that's the y value. And you plug in that 2 into the function here, and it'll spit you out the 4 back in, right? Because functions, inverse functions undo each other's work. That's cool. That's x. I think that's all we need to get ourselves to calculus. This is so cool. So on the next page, that's the remembrance from Algebra 2. I'm having fun here. Because I think we know the chain rule. Don't we know the chain rule? That's cool too. Think I like that as well. So let's take the derivative of this. How fun is that? So now to calculus. And this is so cool. This is one of those things that just pop out of nowhere and you're like, oh, that's so awesome. And then it opens up a whole new world of calculus. We good? Ready for this? Let's take the derivative of this whole big thing of f inverse of x equal to x. That's what we're doing. We're taking derivative of both sides with respect to x. So let's see how this works. I think the chain rule says this. We take the derivative of the outside function multiplied by, oh, this is going to be fun. You guys ready for this? Derivative of the inside. So we're going to put a parenthesis here, and we're going to put a little slash right here, and then put a parenthesis here. And derivative of x. Ah, that's just 1, right? That's a slope of 1. And this is so funky, because check a look at this here. Do we have a derivative of the inverse function anywhere here? Yeah, it's like right there. It's just sitting there, staring at us. Is that right? So if we divide by what's multiplying it, we just figured out the derivative of an inverse function. I'll just let that sink into your brain right there. We good? And this formula just sort of pops out because you figure, okay, hold on, we know chain rule, and that's the definition of inverse function right there. So why not just take a derivative and see what happens?
You can take derivative of equations, like something that equals something else, you just take derivative of both.
Yep. And we'll get there in the next section. I kind of just skipped a little bit. It's called implicit differentiation. Okay, we good there? So let's call this the inverse function theorem, and let's kind of label it so we have it. Kate, can you go back? Go ahead.
Yeah.
Yep, absolutely. You guys slow me down, okay? Because I get excited about this stuff, and then I go too fast, and then everybody's lost because I'm totally excited. My daughter, she is taking third semester calculus at Cuesta. And so she's looking at three-dimensional pieces because it's called multivariable calculus. So you're trying to deal with curvature of things, trying to find the exact middle of a curve. Then you're trying to find something called the normal of a curve. And it's fun.
My dad, we were driving home the other day, the third derivative of the curve is not, continues to read like it's a jolt, because it doesn't keep going. I was like, what are you talking about? And he said, he was trying to explain it to me, but he said, you don't do that till maybe the end of calculus 3 or calculus 4.
Uh-huh.
He said, every time he drives, he's thinking about that was so funny.
True mathematician here when thinks math all the time. Whenever I watch like Netflix or Prime or something, you know, I'm like, oh, that is so cool. And I see the math in it, and then I should record that and I should give it to him. And then by the time it's all done, like, you know, you finish the movie, you move on to something else, and you're like, okay, that's gone. Okay, so inverse function theorem, we have to write these down because we're going to use these in different ways here. So let f of x be a function. Okay, that is, okay, first of all, it's invertible, which means it does have an inverse, right? No sense. And differentiable. Good. So there's two things here. It has to have an inverse, or else we can't play this game. And it has to be differentiable. And then we have to define it as well with y is equal to the inverse of that f. Okay, the other thing that we're going to do, and the only time this thing does not work is when it's 0. We're good? Because you remember we just formed a reciprocal relationship, right? So you can't have 0 in the bottom of a fraction here. So if that is all true, I have f of x. I can find the inverse of it. I can take the derivative of it. I can define my inverse function itself, and the derivative of it is not equal to 0. Then I have this one, which we wrote down on the previous slide. I can find the derivative of my inverse function based upon that right there. Okay, so that's one way of writing it. Let's do another way. So this is kind of with. All right, we have the ghost phone again. Okay, that's if you define y to be the f inverse of g. Or you could also define it with like this, and this is sometimes a more easier way of defining it since we don't have to write everything down. G of x and it seems like it just saves on notation just a little bit here, that's all.
And this is because the inverse, by like comparing slopes, the inverse is reciprocal.
Yeah, so we compared slopes initially just to say, hey, look at that, those are reciprocals, and then we actually proved it by going back to the definition of inverse function and took derivatives of both sides. Sure, go ahead. I like side questions, go.
How do you know that a function is differentiable? Is it continuous, or are there other, is it always a function not ever be differentiable no matter how you change the space and the ability on it?
Sure. Question, Sadie, is how do you know that something is differentiable? And our function is always differentiable. So we have this little piece here. So functions are differentiable. I'll put DFF, is that okay? And we always say this, continuously say this, it's if it's continuous and smooth. And your book doesn't harp on that, but other calculus textbooks always do it. And my calculus professors, they always said it. Is it continuous? Is it smooth? Is it continuous? Is it smooth?
Is it like, oh, but then we'll have the limit.
Yeah. So continuous just means you can draw it at the same time, right? Smooth breaks down if you have a corner, like absolute value, or we have something called a cusp. It goes like this.
Yeah. But then only coming to the
Uh-huh.
limit. So it's sort of not.
Yeah, and then continuous, we have piecewise functions that went like this. That's a discontinuous one. And then we have asymptotes.
So what is the slope at those down? Can you just not find it?
So again,
What is the instantaneous slope on
this
like,
one right here.
the jag things? On the right with the
They're
smooth.
not smooth.
Oh, these guys.
And
So
they're not smooth. What can you find the slope? Like, what about the
no, we say slope does not exist because your two slopes are coming together, right? And you can't say something's happening right at that point. We could say that's a maximum point. That's still okay. So it is useful in some respect. In fact, when we get to those max and min problems, we actually will say, oh, that's cool. That's what it is. It's a maximum point or minimum point. Okay, we good? Yeah, absolutely, you guys. Ask the questions, even if it's side questions here, because the whole point for you guys is to sort of understand calculus, not go through a lecture.
Can we go back to the theorem super quick?
Uh-huh.
What what's the second one? When would
What's the
we-
second all about? It
Yeah.
just helps us not to write f inverse of x when we already define what the inverse is. So then we can just play around with g of x, f of x. Normal way we write functions in the first place, a lot easier to write the functions and the derivative. In fact, we'll probably use the second notation most of the time.
It's just the same exact thing, just written.
Uh-huh.
Wait, isn't it? Doesn't g of x equal f inverse of x?
So G of X would equal F.
Yeah, I guess we should write it in. So let's do this here. So g of x, kind of if you can want to put that in there like that, that's fine. You're saying that's the inverse. Right? Okay,
So
we
why
good?
do we need the fact that it equals y? That seems like it's not related.
I think it just, they're trying to connect it to a graph. Just say, look, this is still part of a graph. Since we have y equals always usually in terms of graphs. Okay, let's do this here. Let's verify that this works. Good. And then after verifying that, we can move on to actually doing this here. So verify. The inverse function theorem. So we'll do it one way, we'll do another, and then we'll see. Find the derivative of okay, this one's gonna be a long one, right? Because we're verifying something. We're gonna do it two different ways. We're gonna see if it works, and then we go from there. Let's do it the short way first, just because we know it already. The direct way would be like this, right? The derivative of g of x, and then you guys go for it. Something called quotient rule, I believe.
The quotient rule plus.
Minus sign for the quotient rule. Okay, I'm going to go with, let's see, quotient rule is derivative of the top times bottom minus derivative of the bottom times top all over bottom squared. Okay, off to the side, if you guys need to, it's f prime g minus g prime f over g squared. If you need the equation for it. Feeling good? Okay, I'm looking at x, looks like, in parentheses x plus 2 over x squared. How about x minus 2 over x squared? How about a negative 2 over... I think I distribute the negative into that right there, don't I?
Yeah.
When I drop the parentheses. So I got negative 2 over x squared. That's mine. Okay, so now we're going to verify the formula for it. Okay, are we good there? All? That was the easy part. So now we have to somehow set up this formula here. We have to set up the that going to this. That's what I need right there, right? So before I do anything else, I have to find the inverse. I have to find that f of x. So how about this? Let me define f of x to be the inverse g of x. And then back to our algebra days. I think I remember this in the algebra days. In order to find this, or find, actually I should find, we're finding g of x. I'm sorry, find f of x. Back to old algebra days. I think this is the way we did it. We set it equal to y. And we, there you go. Yeah, we switched our x's and y's. And then we solve for y again. That would give us the inverse function. And I'll show you where. Oh yeah, that's so cool. That's where it's used. All right, multiply both sides by y. Are we good there? Yeah. Now move the y over.
equals 2 over x. Oh, no. You divide by x.
I think we factor out the y first, though, right? So you guys, again, slow me down if you need to, okay? Factor out the y. I got x minus 1 equals to 2, and then I'm running out of space. So divide by x minus 1. So I think I am good now. Is that right? Cool. I'm defining my x, my f of x. My f of x is to be 2 over x minus 1, which is the inverse of g. Sweet. I think I'm good there now. Okay, so what does this all mean here? Notice in my formula right here, the g function remains exactly the same, right? It's the f that's being taken the derivative of, right? So I'm actually taking the derivative of the inverse and I'm plugging back in. That's cool. So let's do this. Let's take derivative of f of x. I think we can finally put it together here. So can you tell me what that guy is? In this lesson, we kind of go back and forth a little bit here. And I think towards the end, we're like, oh, that's going to make a lot of sense.
What are we looking for?
We're taking the derivative of f of x. The reason for it is because of this little guy right here. So find me derivative of f of x.
Would be -2 over x minus all that squared. Because you have 0 times x minus 1 and then minus
Oh, cool.
2
Okay, we're good.
times 1.
Yeah.
Okay, derivative of 2 is 0. X minus 1. Minus sign. Then it's going to be the derivative of x minus 1, which is 1, times 2 over x minus 1 to the second. So how about negative 2 over this 1 squared? I think we're good there. Are we good there?
And then you have to put g of x into the x.
Yep. So let's do this here. As you copy down notes, don't just copy them to copy them down, right? You just kind of think as you copy them. Good?
Where did the x go?
It became right over here, you mean?
No, to the left, x minus 1.
It multiplied 0.
Uh,
It disappeared. Okay, so now let's do this. Let's do it in stages so it doesn't get too complicated here. So now we're going to do this. Find me this guy. Since we found the derivative, can you plug in the g of x back into our function? So now I'm going to take the derivative function and plug in g of x into it. That should be fun. G of x is x plus 2 over x. And it's that one right there. So again, we're just verifying to make sure this works. Well, when we actually start using it, it'll be a lot faster. But this is just kind of just to prove it. Okay. Say again, Sadie.
Well, are you, oh, you're, okay, we're simplifying.
I'm simplifying, yeah. I'm simplifying, and then I'm going to take the reciprocal of it afterwards here. So this is going to be x. This is x plus 2 minus x to the second. And I think I am good with, let's see, x's are gone. I think I have this on my hands.
how did we get all that stuff on the bottom?
We plugged in the g of x in
Which
for x.
was x plus 2 over x.
Mm-hmm.
So,
Yeah, sure, go ahead, good.
so
Use-
f of x is 2 over x minus 1, but instead of using x, we put in the x plus 2.
x plus 2 over x, yeah, which is the g function, Okay, I think we're good there. Let's see, and I'm going to change it to a multiplication problem by doing this. And the 4 and the 2 reduced down, so I got myself, looks like that. Whew, almost there, almost there. In proofs and stuff like that, in mathematics, what we do, and we put this little triangle, it's like a triangle with little dots onto it. It just means therefore, or then, or because of, or in conclusion. So like therefore.
How come the bottom part's being squared and the top is negative? Wait, or, oh, because you're plugging it into the.
Wait a second, we have to do times g of x, don't we? Or times g prime of x.
Ah, no. So that's the thing. We only did that because when we were doing it initially, we knew the chain rule. So let's see. Let's go back to two things here. So first of all, does this guy here match up to what we just did earlier with the quotient rule?
Yes.
Yeah, absolutely.
Oh, we're just verifying.
Mm-hmm.
We're not trying to, okay, I see.
Yeah, and we don't need the chain rule because the chain rule just proved the fact that it's just a reciprocal of the derivative of the original function.
Yeah, I see.
Okay, are we good? Okay.
We just ended with negative x squared over 2, but then you wrote negative 2 over x squared.
Because let's see, we did this to simplify, and then we said
Oh, it was 1 over the, oh, okay.
the reciprocal of that value. Okay, talk to me.
Why is it the reciprocal?
Let's go back over here because of this formula here. So we just did everything in parts. We found the derivative of f of x, and then we plugged in g of x into it, and then we took the reciprocal. So all of it's on the next page. So we found the derivative of f of x first. That was the first step to do. We're good. Then we found the derivative of f with g of x included in it. And then we took the reciprocal at the end. And it verified, it works both ways, at least that one problem. But yeah, it works all the time.
It's 1 over that. So,
Where does the reciprocal relationship come from?
well, because we had that rule, we just did, right? But the inverse function here.
Yeah.
The reciprocal nature of it comes from the proof itself, right? It goes all the way here.
I'm trying to say, do the derivative of that, but that is what the derivative equals. You're not taking the derivative of that.
Cool, yeah. Does that make sense, you guys? Important just to note. So when you're saying I want the derivative of the inverse function, what you're doing is you're taking the derivative of the original function, plugging in the inverse, taking reciprocal. Let's do two problems. Let's do one or two problems here with this here. So that was just verifying. We got the same thing twice, right? Here's quotient rule. Here is inverse.
We just use the quotient rule then. Because
Good.
That's
Love it.
pretty easy.
I love when questions come up like that. So you guys talk to me. So far, remember how we took derivatives of, easy one. Derivative of just x squared, right? The derivative, I don't need to write this down. This is the setup for the next problem here. What's the derivative of x squared? 2x, because we have a rule. We have a power rule, right? We have a power rule that says if this guy is an integer, because we did it for integers, remember, because we start off with polynomials, right? Then what we can do is we can just take that power, the integer, stick it in front, subtract 1 from the power itself, and voila, we have ourselves a derivative, right? So now the question is this. Find the derivative of that. So We've never done this before.
I didn't remember what that even means.
Okay.
So then if we can do the derivative, we use the other rule, then we don't have to do it, we can just.
Like the cube root.
It's the cube root, yeah. So cube root of x. The only problem is, guys, real quick here, we only have rules for integers for power rule. We don't have rules for anything else. So here's where the inverse function, it just opens up a whole new world of calculus. We good? Once we set this up. So let's work it. I think you actually will find it much easier to do once you kind of use them here. So we're stuck. Can't go with this because we can't use. So if you want to write it a different way, it looks like this, x to the 1/3.
Find the inverse, then we can do that rule, we don't have to deal with this.
Yes, okay, so real quickly here, what is the inverse? What's the f of x? What's the inverse function for x cubed?
Isn't it just like x squared to square root of x, so x cubed is, or cube root of x.
Yeah, so this is the cube root, right? To undo a cube root, you're going to cube it, right? Yeah, if you're going to root it, you're going to take the power of it. And so if you're saying to yourself this, what do I do to this guy to get me back to x? Instead of taking a third power, we're going to take a power of 3 right here, right? So that's the inverse function right there. So we're going to go with x cubed. Oh, nice. Does that look like an integer?
Just
Sure. So we should notice a few things here. Let's do that. Let's do that. So that's one way of doing it, just kind of seeing it, right? The other way of doing it is actually to translate it to y equals cube root of x, right? Switch the x's and y's and solve for y. What would you do to solve for y? And so this case, you're going to take third power, and you got yourself what you want out of it. Good question. I didn't even think that would come up here. Okay, I got that now. Derivative of, so talk to me, derivative of f. Okay.
Cube root x into x squared.
Let's go with it here. So 3. The function itself is the cube root of x, right? Squared. And simplifying this all out, let's see what we got here. We got ourselves, I guess we can leave it like that. Let's see. I just hate the roots and all that stuff. So let me do it like this here. Let me go just this. I like dealing with powers, a lot easier. Okay, so I got the derivative of f. I got the plugged in original value in derivative of f, and then therefore 1 over all this good stuff is going to be 1 over 3x cubed. Oh, that's no fun. So I guess I could leave it like that, or I could write it as, that'll be okay there. Okay, let it sink in. Are we good there? So the question comes up, and you should maybe ask here. So Mr. Ngio, hold your horses. Hold on. So what I just found out, I found out that the derivative of g of x, technically, right, is 1/3 x to the negative 2/3. Is that right? Everybody agree? That's what I just found. Because that's what this means right here, right? So if that little formula means I just took the derivative of the inverse function, right? Or took the derivative function. So then wait. Hold on. If I go back over here and I do this, and I take the derivative using my power rules that I normally do, what's 1/3 sticks out in front? Is that 1/3? X, and then what's 1/3 minus 1? Negative 2/3. Everybody agree?
Yes, so why don't we just do that?
Oh, you know,
That is
that's no
so much
fun.
simpler.
So here's a few things here that come up. First things first is the inverse theorem on the theoretical level of calculus. We good? The inverse theorem allows us to start doing that. We good? Because up until then, we can only do integers, and notice we did integers here, right? Until we notice this little pattern here. The fact that that is actually the same thing as taking it directly. So can you take the derivative of fractions in the exponent? Yes, because of the inverse function. You good?
Oh, but
It's the same formula.
It's the same formula, absolutely. But
We
here,
only know it's possible because of the theorem.
yeah, we in fact,
That's so
Can we
annoying.
prove it directly?
yeah, here it
Without
is.
using the-
Well,
We have to use an inverse function. Can
sure.
we do it without doing the inverse theorem?
Sure, two things happening here. So once we did this, once I showed you this, now yes, you can do it directly. We good? So we're not going to do this whole thing for that, right? Theoretically in mathematics, we're able to do this because of the proof that comes from inverse function theorem. Are we good? So how to show you the proof first, I want to tell you where it comes from, and then you're like saying, Mr. NGA, you know what? That's not cool because you made us waste a whole 50 minutes to show us something that really we don't need. Maybe. Or maybe not, we'll see.
Can we do it without the inverse?
So now because we did it this way and we verified it, then yes, now you can do it without the
But
inverse.
could we prove it without having the inverse?
You cannot prove it without. So you need
That's
that,
funny, it seems like,
you need
so
the inverse function to prove it, but now you can start using it.
so it's not, you're not actually doing the same thing as you do with the exponent rules when it's a integer. It's kind of, you're secretly doing the integer function, it just happens to be the same sort of thing you do.
Absolutely.
It's not related.
Yeah, just like in chemistry.
Is there a test today?
Should not be, no.
No, that's just like one of those big sirens, isn't
Yeah,
it?
Uh-huh. It's going down.
it doesn't sound like the.
That was really loud though.
Usually they
It's
don't
like a
just
piece of machinery or something? Because if it was a siren, it would be coming back again.
yeah, they do this long.
Yeah, I thought it usually happens in August or something.
That's when the siren test is.
Yeah, siren test is
Yeah.
usually in August.
But it might be like. There's
Oops,
other
my
alerts,
elbow.
like- So it might be some other type of thing.
Okay. We're good. So let's do this here. We'll figure out what's happening in a little bit here. Let's go with exercise, what is it, 2?
I think that we technically already did one, so we have 2 ones, but because remember how the
Oh.
verification was 1 is a little last. one was
That's right,
technically
yeah.
2,
This one,
so-
technically, yeah. This is 2. So now we're on 3. So find the derivative of this one. Find the derivative of, I'm just gonna put y in here. Let's see. Yeah, let's do, I'm gonna call it fx. f of x is equal to, and then, okay, now you can do it directly. We good? All yours for directly. And then But we're not done with the inverse function theorem yet because we just might be able to do some other stuff with it. So no, I didn't do it uselessly. I tried not to waste your time for an hour.
It's not
There-
useless because it's making it sure they're actually belong.
No,
Okay,
it's not useless at all.
okay.
So should we go with the long way for this one?
No, do it the short way and go and be done. That's gonna be what? What is 16 times 7 anyways?
I think it's 112.
So this 112.
Yeah, 112.
112, okay. 112 divided by 3 equal to what, 4/3 now?
Yeah.
Done, love it. Love things easier. You know, it's almost like, you know how we did the definition of derivative, right? We used to do the definition of derivative, that little quotient, but once we learn that, then we move on to say, oh, hold on. That means I know this, right? And then once we learned, we did it the long way with sine going to cosine, right? Then we were like, okay, drop that rule. We know that sine goes to cosine. So we're just making things faster, making things go that way. Let's see, how much are 15 minutes left here? Yeah, we should stop. We'll go from there. Okay, and I'll introduce one piece there. Okay, so let's do this here as we always doing this. Find the equation of the tangent line. Remember that little tangent line to the graph of So find the equation of the tangent line to the graph of y is equal to x to the 2/3 at x equals 8. And so all right, and let me kind of just talk as you guys can maybe do it yourself already here. So whenever I say equation of tangent line, whenever I say that, this little formula should just pop up in your head right away from Algebra 1. And then we need to find our y value. We know the x value already, that's 8. That's good enough for us. So then we jump in and we just say to ourselves, okay, hold on. So what's the y value if x is equal to 8?
4.
I think I like 4, yeah. So the cube root of 8 is 2. And 2 squared is 4, and we're good. Okay. Now the tough part. Okay, I got this one. I got the x.
That's the,
Good, Kate.
wait, so m is the derivative?
And this is slope.
So yeah, m is this. Good, Eli. Good.
No.
Good. So in the algebra 1 equation, right? It's the slope, right? But what we are able to do in algebra 1, what we did is we did this. We found the point here, and we figured out the slope between them, right? In calculus, what we're trying to do is we're trying to find the slope at that exact point. So that's the difference there. So that m value takes upon a different meaning. It's not the slope between 2 points. It is the derivative at that single point. So now it's called the instantaneous slope, not the average slope. Good there? Okay. Cool. Okay, so let's do this here. Let's start taking the derivative. Notice that on the left side of it, there's a y value, right? So when we do this here, let's do it. Let me give you some notation just for you guys to see it here. So if y is equal to x to the 2/3, that means dy dx, good, is equal to, as I just took the derivative here, I'm saying, okay, I'm taking the derivative of y with respect to x. This is going to be 2/3 x to the negative 1/3. Are we good? Okay, that's one set of notation. Sadie, I just want to sort of show you the notation here. So if you have a y value, we say dy dx. And then if you want to evaluate something, then on the next loop around, you go like this. You say dy dx evaluated, that little big bar line means evaluated, and that guy needs to go down, at x is equal to 8. So then all this means is you just plug in that little 8 there.
To find the slope.
And that will be our slope for this line here. So let's go with it here. Oh, I don't like negative exponents, first of all. So let me bring this down to the bottom. The 1/3 power. And so this just means the cube root of 8, is that right? Which really is just 2. And are we okay with the 1/3 there? So that is our slope. So maybe let's write this in. M is equal to 1/3 for us. And there's our 3 things that we need. Can you guys finish off the problem? Ooh, just enough to get us to a fun part. Okay, talk to me. Anybody need to have a question of where things are coming from? Are we all good? So the x came from because it said it in the problem itself, right? Good. That's what we got over here. The y comes from us plugging in the x to get our y value. So this is technically x sub 1 is equal to 8. Y sub 1 is equal to 4. We're good? And our slope, the one that we want, which is the instantaneous slope, is 1/3.
Are we done?
So we have everything we need to plug into y1, m, and x1 to get our equation. We're good? So multiple parts here. So I got y minus 4, 1/3, x minus 8, and just real quick like, distribute the 1/3, add the 4 to both sides, which is technically what, 12 over 3? Okay, I'll stop there. Good. Boom. Good. Okay, we should write down the, so I haven't told you this yet here, but power rule of rational functions here. So remember we have the power rule for integers, right? You just stick the n out in front and you go from there. But just for you guys to have it in for your notes, even though it works just like the power function here. So in the book, it kind of divides it into 2 different pieces. First, it divides the whole concept of a unit fraction. A unit fraction, that little 1n, 1 over 3, 1 over 4, 1 over 7, whatever it is, that goes in here, and then it's 1n minus 1. And I'm not sure why textbooks distinguish many times between the unit fraction and the any kind of fraction. So that's the unit fraction. That's like 1/3, 1/5, 1/8.
Oh, so then we have like another variable instead of 1. So
Yeah, and then this one is just any fraction whatsoever. So it's m over n, doesn't matter what it is. It's that, and it's this to the m minus n over minus 1.
I don't see how those are any different. They're-
Yeah, I'm not sure why they distinguish between the two. I have no clue why that is, so.
Well, the equation is the same either way, because you should replace m with 1. And then
Yeah, correct, But in math, they always give you the, whenever you deal with fraction, they always give you the unit one, and then they give you the mixed one. Okay, we have just enough time to hit the cool stuff as well. So inverse functions, yes, we get to this one, now we get to do it the direct way, but the proof comes from the inverse. The only problem is when you take the derivatives of inverse trig functions. Do you guys remember those? And we'll probably have just enough time to do one.
So
Seven.
like sine -1.
Yes, so an example would be sine -1 of x. Boom, there's that one. Okay, let's just quickly, let's review how we got there in the first place, because we'll need these pieces here. Okay, back to the regular one. Sine of x, we're good? How we got there was the sine curve goes like this. Like this. And we go like that.
You have to cut it.
And we have to cut it. We have to limit our domain. Where to where?
Down to from 1 or from 0 either direction. Those or wait, no, it's yeah, you find them two out and find them two out.
Yes, correct. So in order for this guy to pass the horizontal line test, remember that guy?
So between there,
Yeah,
there's
so
pi
we're
over
gonna-
2 and pi over 2.
Perfect. We're gonna chop this off right here. So negative pi over 2. And we're gonna chop off, and usually it goes from, again, notice it goes from the lowest to highest, right? And that's all we need because the rest of it repeats itself. Okay, this is from trig stuff. Oh, and the minimum point is -1. The maximum point is 1, right? So then what happens here is if we want to actually do the inverse, so let's go over here. So then we have this graph. Let's see if we remember it from a long time ago. So we switch things out now, right? So the x's and y switch. So this time we're out to 1, we're out to -1. And it just becomes a little bit longer. It goes like this. And then the maximum value is pi over 2, and the minimum value is -pi over 2. There's our inverse function. Way different. It's a totally separate graph, right? It's different. Okay, that's one thing we need to know. Hey, Zach. I'm going to try to do this in 5 minutes here. Let's go with it here. So now do you guys remember the definitions of the trig function? So we need the graphs themselves. That's the inverse function. That's how we got it, right? And then we have two separate definitions for trig functions here. First things first is the generic definition. That's theta. This is the y, x, and this is r. And we have these little y, x. And then the definition for sine of theta is y over r. Okay, and then we had the easier definition. And all we just did is we made r to be a 1. That was it. And that made a lot of things a lot simpler, easier to calculate. So in this case, sine theta was equal to just the y coordinate. That's right. So then if you go backwards on it, hold on, if you go backwards on it, so that means that theta is equal to the sine inverse of the y coordinate. Is that right? Man, lots of things here. So, and then one more itsy bitsy thing. If we're in quadrant 1, is this okay to say the y is the same thing as y here? Right? Because it's a positive value, we're in quadrant 1. The height of y is going to be the y coordinate.
Yeah.
Okay. I think we got what we need here. And then we get to use it. So, yeah, I think we'll get through just want to show you the fun stuff here before we leave. For the weekend, you can mulch it over.
Yeah, we won't see you till next Wednesday.
Next Wednesday, a whole week to munch on this here.
So much homework to do.
Yeah, so if I do this, so whenever I see y inverse, right, of whatever this is right here, that's going to go right here, right? This is a connection right there, right? If this was a star, it would be a star over here, right? If this was a p-value, this would be a p-value here, right? It's the same thing.
So
Okay.
the second graph is the inverse of the first graph?
No. The second graph is the same thing except r is equal to 1. So whenever we are the ones that are allowed to set up our x and y points,
Always make it 1.
yeah, we can diminish it down to a 1 for r is equal to 1.
That's-
Okay, let's jam. So here it is. The inverse sine. Again, once we build this, we can use that equation, right? Once we build it, we use that equation. That's how we're going to do it. So I'm going to go with define g of x. I think I know what this means. G of x is this guy. So first things first, can I take the derivative of g of x directly? No, not right now. I have no clue how this works, right? There's no, what does this even mean, right?
So we can do sine inverse sine of x, 1 over sine inverse sine of x, and use that one.
Yeah, what is the inverse of the inverse sine? Just sine. Eli, I agree. This is just this right here. Now, do we know how to take the derivative of sine?
Yes.
Yes.
Oh, yeah. Okay.
I'm confused about when we just like write another function,
Say again. When you write, sure.
like, do they come from anywhere?
Yeah. So if you want the inverse, of the inverse, it's going to be just the function itself.
Okay,
Right? So
so,
you're undoing the inverse stuff.
and we just labeled it as that.
Yeah, I'm just saying, hey, this is going to be this. Okay, so I got that. We got a minute and a half. So I'm going to go this quickly. Derivative is cosine. Boom.
We put in
The derivative of the original function. Sine inverse, is that right? So we have this.
cosine and sine.
Oh yeah, do you guys remember doing this stuff in trig class? Where you had one trig function inside the other trig function? One person, all right. Should I keep you in suspense or should we finish it? What do you guys say?
This looks like a chain.
I know what we do, but I can't remember.
Okay, so here's what we're gonna do, ready?
Sine and-
We're gonna set up our triangle again. Our triangle is defined to be a
Oh, yeah, inverse of
R is
sine
equal to
theta,
1.
So it's just cosine theta, right?
cosine theta is, let's see this. This is,
The inverse of sine is
Yeah.
theta, so it's cosine theta.
yes, and then what we're gonna do, we're gonna try to take the cosine of it. We're good?
Yeah, cosine of theta.
So let's do this here. Sine is opposite
Opposite, yeah.
over hypotenuse, right?
Yeah.
Cosine is
Adjacent.
adjacent over hypotenuse. Okay, so how about this? The x goes here, is that right?
Yeah.
Can you guys tell me what this guy was gonna be right here?
Wow.
No? What's the formula? If I have x over here and 1 over here, what's gonna give me the adjacent side? Is that Miss Bear over there?
We could use
Tangent, yeah, so x over 1.
Let's see, how about this?
No,
If
not
onto the side, I'm gonna say this. I'm gonna
we
say
have to use
that little number,
Tangent.
that little number squared plus that number squared will give me that number squared. Is that right?
Yes,
What's the number?
What's the
1 minus x squared.
And then that number becomes,
1 minus x
squared of 1.
good there?
squared, yeah.
So if that's the case, this guy is 1 minus x squared, right?
Yeah.
So I got that one based upon this. Adjacent over hypotenuse gets me
That over 1.
that over 1. And the reciprocal is,
You watched like 17 steps ago.
sorry, I'm gonna finish up. The reciprocal is this. And I'm gonna just blow your mind with that. that is the derivative of,
Wait, of sine inverse, or is that?
It's,
so I'm gonna write this in and we'll just stop there because I'm over time.
Are we expected to just know that? Because-
We'll memorize them by now. The derivative of sine inverse is that
Oh, so
right
it's the
there.
derivative of- Okay,
We stop there because we're
Yeah.
totally over time.
that makes ish.
Ms. Bear, I'm so sorry. Coming in. It's